For centuries, classical optics relied on the accumulation of phase as light traveled through bulky, curved media to manipulate light precisely, such as focusing an image or correcting aberrations. Engineers were forced to stack multiple thick glass elements, resulting in heavy, complex, and space-consuming systems. This material-limited approach is now being superseded by a field called meta-optics, a field that utilizes ultra-thin, flat surfaces to achieve unprecedented control over electromagnetic waves. The shift from bulk glass to meta-surfaces is driven by three primary advantages, those being, first, size. Meta devices are nanoscopic in thickness, typically ranging from 800 nanometers to 1500 nanometers, while the lateral diameter of a device, such as a gallium nitride, a GaN-based meta-lens, may be approximately 50 nanometers, roughly the width of a human hair. Its profile is thousands of times thinner than traditional refractive lenses. Second, weight. By replacing volumetric glass with flat nanostructures, meta-optics drastically reduces the weight of optical assemblies, a critical factor for aerospace sensor and wearable technology. The third is light manipulation ability. Unlike natural materials with fixed refractive indices, metasurfaces can be engineered to possess unique properties, allowing them to perform complex functions like broadband achromatic focusing or multi-dimensional light sorting. Metasurfaces are artificial arrays of meta-atoms, sub-wavelength building blocks that act as a secondary point light source, governed by Huygens' principle. By precisely controlling the phase, amplitude, and polarization of these meta-atoms, we're effectively reprogramming the path of every individual photon. Think of a traditional lens as a massive, blunt instrument that bends light through its sheer volume. In contrast, a metasurface is a microscopic, choreographed lattice. If a standard lens is a heavy door that redirects a breeze by blocking it, a metasurface is a field of billions of microscopic resonators, each catching the wave and pushing it in a specific programmed direction. We are no longer just observing the wavefront, we are reconstructing it at a sub-wavelength scale. The nanoscale is the critical threshold of modern sovereignty. This is the domain where we move from bulky, volume-based optics to surface-based flat optics. This transition is only possible because we have mastered manufacturing at dimensions that defy human intuition. Nanotechnology generally deals with structures sized between 1 to 100 nanometers in at least one dimension and involves developing or modifying materials or devices within that size. What is a nano? A nano is 1/billionth of a meter, or 10 to the negative 9. A normal person can walk 32 kilometers or about 20 miles in one day. If a person were shrunk so that they were 1 nanometer tall, how long would it take them to walk the length of a dollar bill? It would take them 24 years to walk the length of a dollar bill. What is nanotechnology? The science of manipulating atoms and molecules to make new materials and devices. It's interdisciplinary, where science and engineering interconnect. It occurs at the 1 to 100 nanometer range. 1 nanometer is 10 to the negative 9 meters, or about 3 atoms long. For comparison, a human hair is about 60 to 80,000 nanometers wide. Compared to a human hair is about 100,000 nanometers wide. Here's an iPhone processor versus a human hair under a microscope. To put this into perspective, a single meta-atom can have a minimum width of just 50 nanometers. That is roughly 1/2000th the width of a human hair. These structures, often standing 800 nanometers tall, are thinner than a single biological cell, yet they can outperform pounds of precision ground glass. So what? So what is the collapse of the volume to performance ratio? What we're seeing is the rise of GaN-based achromatic meta-lenses that provide full-color, diffraction-limited imaging across the entire visible spectrum. It's not just a lab curiosity. These are direct chip-level replacements for military-grade glass. We can now deploy high-performance imaging systems on platforms previously too small or weight-sensitive to carry them, from swarming microdrones to high-altitude reconnaissance satellites. However, as these arrays grow in complexity, we reach a limit where human design fails. We need an engine that can navigate the infinite. The surface of a meta device is populated by an array of nanostructures known as meta-atoms. Grounded in Huygens' principle, each meta-atom acts as a secondary point light source. When an incident wave hits the metasurface, these structures capture the energy and re-radiate new electromagnetic waves, allowing the device to reconstruct an entirely new wavefront. By precisely designing the geometry and arrangement of these meta-atoms, we can manipulate three fundamental properties of light. First is phase. By controlling the local delay of re-radiated waves, we can steer or focus light. This allows us to create lenses that are perfectly flat, yet focus light with diffraction-limited precision. Second is amplitude. We can modulate the strength or brightness of the light passing through specific points. This enables high-contrast holographic displays and sophisticated optical filters. The third, polarization. Meta-atoms can be designed to vibrate in specific directions, changing the orientation of light. This is vital for advanced medical imaging and secure anti-counterfeiting technologies. Engineers select materials based on desired physical mechanisms and the environment in which the device will operate. The two primary types of metasurfaces are, first, plasmonic or metallic metasurfaces. These rely on the oscillation of surface-free electrons in metals such as gold or silver. Benefits include strong mode confinement and high field enhancement, ideal for sensing. Some drawbacks: they suffer from ohmic losses when metal converts light to heat, typically limited to reflective devices. On the other hand, we have dielectric metasurfaces. These are based on me theory, where high index materials support both electric and magnetic resonances. Some benefits for dielectric metasurfaces include very low loss and high transparency. They allow for a full 2 pi or 360 degrees phase shift without metal absorption. Drawbacks include that they can be more complex to design, as they require overlapping resonances to maintain high efficiency. A specialized dielectric approach is the Huygens metasurface. By designing nanoparticles to generate overlapping electric and magnetic dipoles of equal strength, often through the internal generation of circular displacement currents, designers can achieve 360-degree phase control while maintaining near-perfect transparency. This material selection is the first step toward the specific design methods used to achieve full light control. The Pancharatnam-Berry, or PB phase, also called a geometric phase, is one of the most elegant and widely used design strategies in meta-optics. Its popularity stems from two defining features. The first, material independence. Unlike resonance-based designs, it works with any anisotropic material, such as metal or dielectric. Second, orientation-based tuning. The phase is not controlled by the size of the structure, but by its rotation. Designers utilize the rotation trick to map the phase gradient according to the mathematical relationship where phi equals 20. The phase shift phi is exactly double the orientation angle theta of the meta-atom. Therefore, by simply varying the orientation of an identical meta-atom from 0 to pi in radians, which is 0 to 180 degrees, we achieve a full 2 pi or 360 degree phase shift. This simplifies the layout process significantly, as a single high-performance shape can be used repeatedly across the entire device. Once the design is mapped, the theoretical layout is ready to be moved into the physical fabrication phase. The life cycle of a meta device follows a precise sequence. Material selection proceeding to meta-atom design, then proceeding to phase distribution, next to layout, then to fabrication, finally to characterization. The layout step is where the rotation and placement patterns are translated into CAD files for nanolithography tools. Primary fabrication technologies include photolithography, using a mask and light to transfer patterns, electron beam lithography, EBL. This is a maskless process using focused electrons to write designs directly. Focused ion beam, FIB, strips away surface atoms with an ion beam. Nano imprinting mechanically stamps a pattern into a soft, curable resist. Laser direct writing uses a focused laser to induce localized changes or damage on a surface. The last is 3D printing or additive manufacturing. Build structure layer by layer. Alright, so here's what most people miss about this. In October 2011, the first Metasurface designs were proposed. So a couple months later, in 2012, the AlexNet revolution transformed artificial intelligence. These two fields grew in lockstep because they needed each other. Human intuition can't design a surface with billions of unique meta-atoms. They have different designs and optimization strategies for hardware. But AI is capable of doing these advanced mathematical optimization problems. Human design is a forward problem. We try a shape and we see what it does. This is slow and limited. Strategic technological dominance now relies on surrogate modeling and inverse design. The speedups are staggering. While traditional Maxwell solvers might take hours to simulate a complex structure, AI-driven surrogate modeling provides a shortcut that's about 600 times faster. So when we move to CNN-based freeform design, we see close to a 9,000 times multiplication increase in speed. This is a force multiplier that allows us to move from a requirement to a finished design in milliseconds. The tandem strategy is their secret weapon. By cascading an inverse network with a pre-trained forward network, we can ensure that the AI converges on a physically viable solution. This allows for on-demand development of triple band absorbers or chirality-specific filters. AI has effectively lowered the barrier to entry, allowing any actor with sufficient data and computing power to design world-class photonic hardware. To design a meta-atom, we have to understand the precise interaction between light and matter. Traditionally, this requires solving what are known as Maxwell's equations. This is the same James Clerk Maxwell with Maxwell's demon thought experiment, interestingly enough. While these equations provide an exact ground truth, they are computationally expensive and very kind of hard, grueling to solve for complex, non-intuitive geometries. Traditional full-wave numerical solvers, such as the finite difference time domain, FDTD, the finite element method, FEM, and the rigorous coupled wave analysis, RCWA. Those are incredibly time expensive. When exploring freeform structures with near infinite geometric possibilities, traversing the design space to find the right shape can take months or even years of processing time. So in a tandem strategy, you have the inverse path, in this case, neural network 1. Then you have the forward path, neural network 2. The first inverse neural network 1 maps the target optical response to candidate geometric parameters. A second neural network, this one the forward path, a pre-trained fixed weight surrogate model that predicts the response of the candidate geometry generated by the first inverse neural network 1. So the steps that they use to do this: independent forward thinking, train neural network 2 as a standalone surrogate model until it achieves high accuracy, that being over 99% in predicting spectra from geometry. 2, weight fixation. The weights of neural network 2 must be frozen or fixed. They will not be updated during the inverse training phase. 3, tandem coupling. Connect the output of neural network 1, the predicted geometry, directly to the input of the fixed neural network 2. And the last step, step 4, is back propagation. Calculate the losses by comparing the original target spectrum, which was the input to neural network 1, with the predicted spectrum, the output of neural network 2. Because neural network 2's weights are fixed, the back propagation must pass through neural network 2 to update only the weights of neural network 1. This forces neural network 1 to find a unique, physically consistent geometric solution. While tandem neural networks provide stable convergence for predefined shape parameters, generative models are required for the de novo synthesis for high degree of freedom freeform structure designs. First, we're going to look at generative models. Generative models transition the design process from selecting parameters to exploring a continuous latent space, a compressed database of all possible topologies. VAE is a variational autoencoder, a VAE, an optical synthesis. VAEs use an encoder to compress high-dimensional geometry into Gaussian distributed latent vectors, latent space mapping. By sampling this latent space, we can generate unseen geometries that maintain specific optical attributes. Composite crossed architectures. For complex phenomena like in bound states in the continuum, BICs, we employ a composite crossed architecture. This involves a VAE combined with a convolutional neural network CNN that reads out the BIC frequencies from the latent vector Z, allowing for the precise design of high Q resonances from freeform patterns. We also have a generative adversarial network, a GAN. Generative adversarial networks employ a zero-sum game between a generator and a discriminator, a critic. The discriminator's primary role is to ensure the generated patterns match the probability distribution of viable meta-atoms. This prevents the generator from producing physically impossible noise patterns or jagged structures that can't be etched. Conditional generative adversarial networks, or CGAN, by introducing the target spectrum as a conditional variable. CGANs enable on-demand design. The network produces the topology that best fits the demanding input spectra, often discovering novel geometries that elude human intuition. So transitioning from the gradient-based methods, we also have evolutionary computation, or digital Darwinism. Evolutionary computation excels where objective functions are non-differentiable, or when the design space is prone to local optima that trap gradient-based deep learning models. Evolutionary toolsets used in meta-optics, first genetic algorithms, utilizes crossover and mutation to optimize pixelated coding metasurfaces. GA is highly effective for broadening the bandwidth of microwave absorbers. We have particle swarm optimization, PSO, tracks the personal best and global best positions. PSO is the standard for designing achromatic metalenses and folded optics spectrometers, where the global efficiency maximum is the primary goal. You have ant colony optimization, ACO, and Malaco, multi-objective lazy ant colony optimization, Malaco. That is specifically suited for 3D topology optimization, a critical performance benchmark. Computational load of genetic algorithms, GA, increases exponentially with the number of grids, while the load of Malaco increases linearly. This makes Malaco the only viable choice for complex, tortuous 3D nanostructures. The idea is that these different strategies can be used together. Modern workflows often combine VAEs with evolution strategies. In this model, the VAE defines the genotype, the latent vector, while the evolutionary strategies model performs the selection. This alleviates local optima issues by combining rapid topology generation with robust global search. Engineering constraints and fabrication realities. The most sophisticated AI-generated design is effectively useless if it cannot be manufactured. We must account for the gap between a pixel-level digital design and the physical feasibility of its fabrication. So here we have some of the constraints and applications in fabrication. So the first we're looking at is electron beam lithography. The key constraints is that it has a slow throughput, high resolution, approximately 10 nanometers. Primary applications, research-grade meta-optics, focused ion beam, direct carving, simultaneous etching. It can be used for 3D chiral structures. We have nano imprinting, requires high-quality mold, high throughput. Mass production of meta devices, 3D printing, 2pp, limited by voxel size, additive flexibility, primary application in rapid 3D prototyping. In terms of material selection and discretion, for the visible spectrum, TiO2, which is titanium dioxide, or GaN, which is kind of confusing. This is the chemical or molecule, gallium nitride. So in the visible spectrum, titanium dioxide and gallium nitride are used sometimes due to their low loss, high index properties. For NIR, silicon is preferred. Architects must avoid plasmonic, metallic metasurfaces for transmission applications due to prohibitive ohmic losses. Metal should be restricted to reflective or resonance-specific designs. For smoothing and thresholding, AI outputs, especially from generative adversarial networks, often exhibit jagged edges. Pixel sizes below 10 nanometers are generally unmanufacturable. Pixel sizes below 10 nanometers are generally unmanufacturable. Post-processing, smoothing, and thresholding are mandatory to ensure the digital pattern can be translated into a stable physical mask. So again, just to recap those two philosophies, the first philosophy is evolutionary computation. Genetic algorithms, evolutionary computation, it doesn't learn from data, it searches for a solution by mimicking the iterative processes of natural selection. The three logic-based stages: initialization, mutation and crossover, and selection. In evolutionary language, that is, biological evolutionary language, the optical design equivalents, a genome would be the binary array or digital code defining a meta-atom's pixels. Mutation, randomly flipping a pixel or dimension to explore new light-matter interactions. The crossover is recombining geometric features of two parent designs to find a superior hybrid, and the fitness value is a mathematical score of how closely the design's response matches the target. The second philosophy, mapping patterns through deep learning. The variables used in the learning framework, the task, the experience, and the performance. What they're really after is the hidden layer. Again, we've covered convolutional neural networks, CNNs, specialized for 2D grid-like images. They process the pixels of a meta-atom to recognize spatial patterns that a human eye might miss. Variational autoencoders. These shrink complex shapes into a latent vector, a simplified digital shorthand, which allows researchers to generate entirely new designs by sampling that hidden code. And then generative adversarial networks, which is a type of competitive game where a generator tries to create fake designs that fool a critic. This results in highly efficient, natural-looking structures. Now, one of the main hurdles is the resonance. While fast, deep learning has a physical limit, networks often struggle at resonance frequencies, where light-matter interaction exhibits sharp non-linearity in these narrow windows. So in certain ranges, it acts kind of weird. Forward and inverse problem. Forward problems predict what a shape does. It's a one-to-one mapping. Inverse problems find a shape for a specific goal. What they do is they mix these two into a kind of a hybrid model that can accomplish great design optimization. So, a comparison of forward and inverse designs. Forward problems are geometry in pixels. They predict how the light interacts. They are simple in terms of complexity, one solution per shape. Surrogate modeling is how AI is used to fix this problem in terms of meta optics. Inverse problem, desired goal. The goal of inverse problems is to discover the physical shape. This has a higher complexity because multiple solutions are possible. And this is where tandem neural networks combining these different strategies comes into play. In terms of our two perspectives, evolutionary, gradient-free, the primary strength is that it finds the global best option. Primary weakness is that it's very slow. It requires constant resimulation. Best used for optimizing a specific high-stakes design. The physical limits is that it's limited by computational time. Now, on the right, we have deep learning, the data-driven model. It has near instant results in milliseconds. Data hungry is the weakness, is that it requires massive training sets. What is it best used for? Rapidly exploring thousands of candidates. The physical limit is that it struggles. The physical limit is that it struggles with sharp non-linear resonances. So what can meta-optics, meta-lenses, meta-atoms, what can this be used for? Well, right now, some of the uses that I found, we have achromatic lenses. These focus all the colors at a single point. Gallium nitride, the primary material used. What AI does is it optimizes meta-molecules to correct for color distortion. High efficiency lenses, designed for maximum light throughput. Titanium dioxide used. AI generates high aspect ratio patterns for 2π, which is 360 degrees phase control. Smart imagers, seeing through obstacles. Silicon is often used. AI reconstructs images from a disordered data set, such as seeing through a 5-centimeter wooden wall. Meta holograms, projects high efficiency 3D images. Plasmonic / metal designs, meta-atoms that is. VAE and GAN models design the binary phase maps for clear noise-free images.
After years of technology development and rigorous testing, our first generation chips are now in commercial deployment. Our product is targeted at enabling solid-state LiDAR. In this market, it's been a long-standing dream to replace the bulky mechanical beam steering devices with a solid-state option. To this end, Lumotive has developed the world's first one-axis, CMOS-based beam steering device, called the LM10. The LM10 is capable of very wide field of view beam steering, up to 160 degrees. Lumotive has also developed a compact method for coupling light onto the LM10 using a prism, and this is typically how our customers deploy the LM10 in their LiDAR systems. This is our demonstration kit, which highlights the full capabilities of the LM10 chip. For the purposes of this demonstration, we beam steer the infrared light onto a special screen, which converts that infrared light into green light so that it can be seen by the human eye. In sweep mode, we see the LCM sweeping our 160-degree total field of view from left to right, dwelling at each angle for the same amount of time. ROI mode showcases how the LCM's programmable beam steering can be used to define certain regions of interest in the field of view, where we would like to spend more time measuring. These regions of interest are completely user-defined and can be changed instantaneously. With this capability, the LCM can interact with its environment in a much more natural way, doing a coarse overview sweep and then tracking specific objects of interest. You could imagine an automotive LiDAR taking advantage of this ability to have two different operating modes. A city driving mode, where you want the full field of view scan for maximum visibility, and a highway driving mode, where you spend most of your time measuring the horizon to gain maximum range. With Lumotive's LCM technology, one system can switch between many operating modes on the fly. We can even send out multiple beams simultaneously to cover more of the field of view at one time. In user mode, we link the LCM steering angle to a touchpad to demonstrate how it offers the ultimate flexibility among beam steering devices. As you can see from this demo, the Lumotive LCM technology represents a new era in programmable optics. For more information, please visit our website at lumotive.com. Thank you for watching.
What about on the security frontier? What would happen if this fell into the hands of extremist or totalitarian-minded people? Technology is dual use by nature, and the Second Order Revolution carries profound risk for global stability. The radicalization of stealth. If broadband anomalous reflection technology falls into the hands of religious radicals or extremists,
Yeah, so the name of this project is FunVax, which is the vaccine for religious fundamentalism.
And you have a proposal already?
The proposal has just been submitted, and I think that the data that I have shown you today would support the development of this project, and we think it has great promise.
Our traditional security perimeters become obsolete. Two-layer planar metasurfaces used by an adversary could render a threat invisible to microwave imaging or radar. This facilitates a form of asymmetric warfare, where the defender is effectively blind to incoming threats. Totalitarian surveillance layer. The biomolecule sensing that was praised for medicine is a potential tool for absolute control. A totalitarian state could deploy high-sensitivity, non-invasive sensors in public spaces to monitor biological markers in real time. More disturbingly, using faster RCNN, which is a convolutional neural network, a faster version of that for region of interest recognition. States can now achieve through-wall microwave imaging and gesture recognition. So even your movements inside your own home are no longer private. They are data points in a state-level recognizer. Or Palantir.
This is Maven Smart System, Palantir's software as a service product that we are deploying across the entire department. As you can see, it's not just one data feed, it's multiple. And instead of having 8 or 9 systems for those decision makers to look at every single day in order for them to make decisions, you then fuse it into a single visualization tool. The single visualization tool allows you to select, deselect different types of data, look at different approaches to data, but more importantly, action from the same system that you're trying to develop your workflows around. Once you have a detection that you want to actually move into a targeting workflow, for example, this is what we do. Left click, right click, left click, magically, it becomes a detection. That detection then gets moved into a workflow. This is standard digitized workflow, but I want to walk you through it quickly. You have different types of targets that are identified on the left there. Every single column produces a different type of decision-making process. Once you have that decision, you're trying to actually action that process, we now move into COA generation, course of action generation, where we are automatically, via a number of factors, trying to identify what the best asset to prosecute a target looks like. Once we've got the different approaches and we select one, we then can move directly into how do we action that target. So we've gone from identifying the target to now coming up with a course of action to now actioning that target, all from one system. This is revolutionary. We were having this done in about 8 or 9 systems where humans were literally moving detections left and right in order to get to our desired end state, in this case, actually closing a kill chain.
Actually closing a kill chain.
Perhaps the greatest risk lies in passive optical logic. By performing and, or, and not operations directly on a metasurface, extremists could create dark communication networks. These systems are entirely passive. They require no power and emit no electronic signature. They are the ultimate meta-technology, immune to standard electronic eavesdropping and interception. So what is the ethical imperative of nano-optics? We stand at a crossroads. Meta-optics offers a path to humanity's higher level, quote-unquote, instantaneous computing and life-saving diagnostics, but it also provides the tools for absolute invisible control. The meta-atom is sub-wavelength, but its impact on the global power structure is massive. To ensure these intelligent optical devices remain in the service of democratic advancement, I propose 3 strategic recommendations for immediate policy action. First, lithographic gatekeeping. We must implement strict international controls on deep ultraviolet, DUV lithography, and nano imprinting tools. These are the choke points of the revolution. He who controls the DUV machines controls the ability to be invisible. Second, biological privacy standards. We must lead the development of international norms regarding the use of high sensitivity, CERA, and microwave imaging. Biological markers and spatial privacy must be protected against state and federal level overreach before the sensors are already in the walls or the paint. Third, an audit of passive logic. We need to establish a framework for identifying and monitoring the development of non-electronic passive optical logic systems to ensure that they are not utilized by extremist cells for untraceable command and control. The light of the future is being shaped today. Let us ensure we are the ones who decide where it shines.